Welcome! In this video I'll show you how to solve problem 2.3 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now this problem states the following. It says, show that there is no acceptable solution to the time-independent Schrödinger equation for the infinite square well with the energy equal to 0 or the energy less than 0. This is of course a special case of the general theorem that we saw in the previous problem, previous 2.2. I also have a video for that. Check the playlist or the link in the description. But this time do it by explicitly solving the Schrödinger equation and showing that you simply cannot meet the boundary conditions. Okay, so let's do it. Let's begin with the case where the energy is equal to 0. So let's keep in mind the Schrödinger equation we know is this, so minus h bar over 2m d squared psi dx squared plus the potential times the wave function is equal to the energy times the wave function. But keep in mind, right, the infinite square well is the case where we have, right, this is a graph of the potential. This is the potential as a function of x. And in this case, there's an infinite potential from 0 to the left and an infinite potential from some a all the way to the right? So we have only this space in here where our wave function could exist. Okay, so in that region, of course, the potential will be 0. And now we're also in the case where the energy is 0, which means that the right-hand side will also be 0. So this means that what we are solving is d squared psi dx squared is equal to 0. Now, this is just a very trivial differential equation. We just need to integrate twice. So when we integrate twice, we get ax plus b, right? Of course, these being constants of normalization. In this case, we will find them with boundary conditions. So let's apply them. What are our boundary conditions? Well, at 0, the wave function has to be 0, right? Because we get to an infinite potential where it cannot exist, and the same at a, right? So at 0 and at a, our potential must be 0. So psi at 0 and psi at a have to be 0. So let's apply them. So psi at 0 means that a times 0 plus b has to be equal to 0. So b has to be equal to 0. All right? So that's the first one. Now psi at a tells us that a times a has to be equal to 0. But a is just a constant. It's like, I don't know, 5 or something. So of course it's not 0. So this means that a also has to be 0. So our wave function is always going to be 0, which of course is not a real thing. That's nothing, right? It's not normalizable. You can't do anything with that. So this is not an acceptable solution. So we can see that for the case where the energy is 0, we simply do not get anything that we can work with, right? It is not normalizable. Okay, now for the next case. So let's go back here. And this time let's go when the energy is negative, right? The energy is smaller than 0. And in this case, we have the Schrödinger equation again, with the potential still being 0. So let's isolate the second derivative, like we always do in these cases, minus 2me over h bar squared psi. And because I don't want to have to write down these bunch of constants all the time, let's define a new constant. Let's say k is going to be the square root, so that this thing will be k squared of 2me over h bar squared. And now the question is, and this is where students make tons of mistakes, do we include the minus sign or not? All right, so how do we choose that? Well, we want this k to be real whenever possible. So would this be real without the minus sign? Well, the energy is negative, right? So that means that as of now, this is a complex number because you would get the square root of a negative number. So if we include this minus sign, we would get a positive quantity because we have minus the whatever negative number the energy is. Okay, so that means that k has to be this entire thing. Okay, just to make it very clear. So that means that we are now solving the second derivative of a psi with respect to x, and there we go. Okay, so how do we solve this differential equation? This is something where a lot of people often get very confused. So the way that I would recommend that you solve this is that you simply first factor out the wave function. right? So you simply write it like this. You leave the wave function out. This is completely equivalent, right? The second derivative acts on it. And then you also multiply by the k squared. So nothing illegal is being done. Now we rewrite this as just a sum times the difference. So d dx plus k, d dx minus k. Now you can't always do this, and I will show you when you can and cannot. So let me just quickly show you, right? And if you're not sure if you can, just multiply through and see that you indeed get the same thing. So to check if this actually works, let's just multiply through, right? So this will help you see the condition where it works and where it doesn't. So first, of course, we get a second derivative with respect to x, and then we get plus k times the space derivative. Then we have minus d dx, and here you have to be a little bit careful, right? Because here we would get k times psi, right? If you just multiply through to get the psi as well, this will make it a bit more clear. So we would get the derivative of k psi, and finally we would get minus k squared times psi, of course, so times psi. So this is equal to 0. Now for both of our expressions to be equivalent, right? So for this to be equivalent to what we have up there, we only want these two terms to survive. So we need that these middle terms cancel out. Now, when does this happen? This happens when k does not depend on x, because in that case, right, we can simply take it out of our derivative. So we get k d psi dx minus k d psi dx, and they cancel out. So we can indeed do the factorization that I just showed you. But if k somehow were to depend on x, then you would not be able to do this, right? So if you are ever in a situation where you want to do this factorization, but your constant k depends on x, I'm afraid that you need to find some other way of doing it. But that's not our problem today, so let's go ahead. Okay, so for this to be true, we need that either this times psi is equal to 0, or this times psi is equal to 0, right? So either d dx plus k acting on psi is equal to 0, or d dx, so let me just write it, or d dx minus k acting on psi will be equal to 0. So those are our two possibilities. So well, here we can just solve this very quickly. So we have d psi dx plus k psi equal to 0. So let's just write this as this is equal to minus k psi. So this is solvable by separation of variables. So we would have d psi over psi. This is equal to minus k dx. So here we can simply, integrate. We just integrate. So we get, well, d psi psi. This is the natural log of psi. This is equal to minus kx plus, well, some constant of integration c. So now we exponentiate this, and we get psi of x is going to be, and now, well, we can put these two together, right? So we get some other constant of integration times e to the minus kx, right? Why did we put them together? Because we have e to the minus kx plus c, which is the same as e to the minus kx times e to the c, but this is a constant, so we just called that constant a. Okay, so this is the solution for this one case. Now let's go for the other case, right? Let's go for this one. Here, of course, it's going to be analogous. The only difference is a minus sign, right? So we get d dx. This is equal to k psi. Oh, there's a psi supposed to be there. We do separation of variables. I'm going to go a little bit faster because it's the exact same thing, except that it's positive. Now we integrate, so we get natural log of psi. This is kx plus some constant. And then we exponentiate, so we get that psi of x will be, this would be kx plus, this is simply some b times e to the kx. Okay, so of course the actual solution is going to be the linear combination of these two. So that means that our solution for this case, let's go back up. This will simply be psi of x is a e to the minus kx plus b e to the kx. Okay, so that is our solution in this case. So with the solution in mind, let's now go ahead and apply the boundary conditions, right? Which are, again, psi of 0 is equal to psi of a, and they are both equal to 0. So let's begin with psi of 0. So at psi of 0, we have that a plus b has to be equal to 0, which means that a has to be equal to minus b. Then at psi of a, for this to be equal to 0, right, let's plug it in, we get a e to the, well, minus ka, so minus ka, and then we have minus a, right, applying that b is minus a, so I used that actually, so b is minus a, e to the ka, okay, and this has to be equal to 0, so that means that a e to the minus ka has to be equal to a e to the ka. So we can, of course, divide by a, and then we just multiply by e to the ka, so that we get that 1 is equal to e to the 2ka, which means that 2ka has to be equal to 0. But 2 and a are simply constants, so they, of course, cannot be 0, so we need k to be 0. Okay. But what does that mean, right? Let's go back to our wave function right here. If k is equal to 0, and we know that b is equal to minus a, then that means that our wave function is a times e to the 0, which is 1, minus a times e to the 0, which is 1. So we get a minus a, which is 0. So again, we had a non-normalizable solution for the Schrödinger equation. So we can see that indeed there is no acceptable solution either for e equals 0 or e negative. So of course, this entire region right there is also prohibited. There is no acceptable solution there. So there we go. I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe, and maybe even consider checking out my Patreon. So I'll see you on the next video. Thank you very much for watching.